Okay, so this talks about how we build an advanced coverage guided fuzzer for program binaries, and here we want to focus on we want to emphasize on program binaries because we want to build fuzzer to find bugs in closed source program, so you can find errors even if you don't have a source code. Okay, so my name is Nguyen and Quynh, and I'm working for one local university in Singapore named Nanyang Technological University. And my main research area is in low-level stuff like operating system, virtual machine, binary analysis. And I happen to be the author of three reversing frameworks, Capstone disassembler, Unicorn emulator, and Keystone assembler.
Hello, my name is Wei Lei. I work in the same university in Singapore as Quynh. Normally I do bug hunting, fuzzing, and bug bounties.
Okay, so here's a program of our talk. First, we look at the background of guided fuzzer, and we introduce an issue on the public guided fuzzer, focus on fuzzing binaries. And you will see why we need to build a new fuzzer ourselves named Darko. And in the next part, we introduce the features of Darko fuzzer and how it was implemented and designed. And after that, we have some screenshots so you can see how it works. And we also introduce some bugs with how it is fuzzer. Actually, Darko fuzzer is still very new. We are at very early phase, but hopefully you can still see something useful. Okay, so a bit about background of the guided fuzzer. So fuzzer is an automated software testing technique, so you can find bugs automatically. And the idea is that you have programs that you want to find bugs inside that program. So you build fuzzer, and you run this program inside the fuzzer. So the fuzzer feeds the graph input to this program, and this program will run this input. And at the same time, when the program runs, the fuzzer tries to monitor the program. And it tries to detect errors like crash, hang, memory leaking, and so on. And in case it finds exploitable bugs like memory corruption or information leaking, then you find some vulnerabilities, right? So the idea on the guided fuzzer, on the fuzzer is that we try to generate the good input. So the input will take the program to many different places in the program. We have very big search space. And the idea is that how to generate the good input so we can maximize the code coverage, and hopefully you can find some bug in some very deep corner in the program. There are a few types of fuzzer. First one is black box fuzzing, and this one's kind of very dumb fuzzer. So this kind of fuzzer is very simple, very easy to build. You just run the program inside this kind of fuzzer, and black box fuzzer just send some totally random input to the program. And black box fuzzer doesn't know what happened inside the program when it runs. And you can see that black box fuzzer is very easy to build, but it's not very effective because it doesn't know how to generate the good input. The other type fuzzer is white box fuzzer. This one is totally different. It's much smarter than black box fuzzer. So for white box fuzzer, they use many advanced program analysis technique to understand how program works. And based on this information, white box fuzzer can generate very good input, and the fuzzer can quickly find some, go to many corners in the program. So the concept of white box fuzzer is very good, but in reality it's not very good because white box fuzzer use many heavy techniques like symbolic execution or model checking, and in reality, it slows down the fuzzer a lot, and that's a huge problem of white box fuzzer. The third type fuzzer is gray box fuzzer, and this is our focus on this talk. There's the name of Gradebook fuzzer is coverage guided fuzzer. So for this kind of fuzzer, we try to build a smarter fuzzer than a black box fuzzer, but we do not use many heavy techniques like white box fuzzer. So the idea of guided fuzzer is that when we run the program inside the fuzzer instrument the program. So we know what's going on when the program runs, right? And based on the feedback from the instrumentation, the fuzzer can generate the better input for the next round when you run the program again with the new input. So we try to repeat on this step, instrumentation, change modify the input, and the fuzzer run. And actually, this kind of fuzzer proved to be very, very effective. It's much smarter than black box fuzzer, but it's much more effective than white box fuzzer because we don't use many, we don't use heavy program analysis technique like white box fuzzer. And in fact, this kind of fuzzer finds a lot of bugs. And one prominent tools of this kind of fuzzer is AFL. And AFL finds a lot of bugs. Okay, so there are quite a few public guided fuzzer which is open source and everybody can get to use. And we list some important one here. AFL, of course, is a very important, very prominent guided fuzzer. So for AFL to work, you need a source code of the program, and after that, you compile the program using some special compiler provided by AFL. And with this instrumentation view, the AFL can work. And in case you don't have source code, AFL also support binary fuzzing. So in case your program is Linux binary, AFL has emulation mode, which uses QEMU inside to emulate the binary. So AFL can actually find bugs in Linux binaries. The problem with AFL is that AFL doesn't work for Windows. So there's an attempt to make AFL work for Windows. And one project is named AFL Quynh. They try to port AFL to Quynh, so it works on Windows. But the problem is that this fuzzer is very slow, very buggy, and actually they stopped development of AFL Quynh for a long time ago. The other type guided fuzzer is WinAFL, which is very new and very good, built by some researcher from Google. WinAFL is basically a Windows fork of AFL. So they fork AFL and rewrite many core parts of the fuzzer so it works on Windows. You can build on Windows and it works on Windows. The main difference between AFL and WinAFL is that WinAFL only supports persistent mode. So the idea is that it only fuzz a part of the program, not the whole program. It's called persistent mode in AFL. The last fuzzer based on AFL is AFL DIN-ins. This one is a bit different. This one, okay, has a program, you want to fuzz it, right? So we need instrumentation. So this fuzzer AFL DIN-ins, they try to modify the program on disk. So they instrument the program and actually really modify the program on disk. And after that, you run the modified program, binaries, inside this kind of fuzzer. This one seems to work, but actually it has many issues with some more complicated program. And AFL DIN-ins doesn't support Windows. Okay, so we can see that there are many issues with public fuzzer if you want to fuzz binaries. You don't have source code, right? So the first issue is that all the public guided fuzzers have very poor support for fuzzing binaries. Like AFL, it works for binaries only if you use emulation mode in AFL, which is based on QEMU. But QEMU has many limitations. And this emulation mode for AFL only works for Linux binaries and nothing else. And in the list of the binary of the fuzzer I introduced in the last slide, only WinAFL support Windows binaries and nothing else. All the guided fuzzers are very tricky to use. For example, look at WinFL. WinFL only support persistent mode. So you can only fuzz a small part of the binaries, not the whole binaries. And the point is that you need to choose which part to fuzz. So you need to reverse the binary. And actually not all the programs support this kind of fuzzing. Because to support this kind of persistent mode fuzzing, you need to choose a path that is stateless. So you can loop back and run the game. And not all the programs support this kind of fuzzing. And we have many issues when we try to use WinFL on some real-world binaries. The other issue is that all the guided fuzzer for binaries has many issues on performance and stability. So for example, WinFL uses Dynamo Rio binary instrumentation frameworks, and it fails to work on many complicated binaries, and it's pretty slow. Dynamo Rio is the best in terms of performance for binary instrumentation, but it's still slow down the programs like 15 to 20 times, and that's too slow. So we are not very happy with all the guided fuzzer public available, and we want to do something better. So that's why we try to build our own fuzzer named Darko.
Try this one. So Darko is the name of the current version of our fuzzer. Before that, we came from a prototype in middle of 2015. So at the time, AFL was released for about a year, and it's so powerful that we all appreciate the power of this fuzzer. But there was no Windows counterpart available at the time. So we tried to port the AFL fuzzing code into Windows, and we need the native instrumentation to work with arbitrary binary. So we built a prototype instrumentation with Quynh. Quynh has a probe mode which offers close to native speed. So we don't use it as a virtual machine because that will slow down quite a bit. The POC works pretty well. We found the real bugs, but it's still not too good. So later we decided to extend this instrumentation framework to more platforms and more architectures. Thanks to this new engine developed by Quynh, we call it Scorpio, is to inject lightweight hooks into program binaries. And using all the reverse engineering trilogies frameworks, we can extend to other architectures or platforms easily. But the first of all is on Windows. We want it to work on Windows. This instrumentation, by nature, it supports selective fuzzing. So if we build a project with AFL instrumentation, we need to do selective instrumentation on interesting parts of the binary. But with this instrumentation, we can choose where we want to fuzz freely. The other one is we also tried persistent mode on binaries that when it's possible to fuzz with persistent mode, similar to other in-memory fuzzing. They keep less global states, so we can loop maybe 100 to 500 times without random crashing. We can incorporate into this framework to speed up the fuzzing quite a bit. We also included other enhancements to AFL, like brute forcing some of the program constructs, like string compare, integer comparisons, and many others that you can break down to brute forceable structures. So the features, Darko is pure software-based, which we mean the instrumentation. Other similar techniques might require hardware support like PMU or Intel PT. So you may have problem running it in a VM that does not support this feature. We want it to be fully portable and cross-platform. Currently, we tested all the native binaries, such as Microsoft binaries or Unix binaries. Okay, so we intend to build it to be fast and stable and to be versatile. And so far it's order of magnitude faster than DBI approach because the Euro emulation of the original binary will slow down quite a bit. Unless, like WinAFL, it works when the DBI approach works together with persistent mode. These two will balance the cost with each other and give a reasonable speed. We do not use DBI approach, so we expect this to be faster, at least close to native speed. When enabled with persistent mode, we expect it to be even faster. On the demo case of WinAFL on GDR+, the measured speed is about 2 times. So I'll come to the implementation. The initial version in 2015 was completely compatible to AFL. In addition, we added concurrency support. We record the program branches in thread local storage on the Windows threads. The initial POC is on AFL Nguyen with the pin probe mode. This version works with all the 32-bit user space binaries. We also built a test case post-processor like AFL does. And this version, although not very fast, it finds real bugs in Adobe Reader and Windows Journal. The difficult part of this approach is actually the static analysis part. So basically where to do this instrumentation when a binary is given. You need to reverse the program structure. Basically, we need the CFG information to know where to instrument. Other features of the implementation, we included all the support necessary for real-world fuzzing, ASLR, and threading. And the current version supports Windows, Linux, and OS X. We are currently implementing x64 and ARM architectures, but for x86, the static analysis and the instrumentation are working fine. So the challenges in static analysis is equivalent to recover the CFG. Because it's actually an open problem, as far as I know, to differentiate code and data. And especially Microsoft compilers sometimes put the virtual function tables and mix them inside the text. And sometimes the disassembler could not differentiate those data. These are actually pointers embedded in code segments. And those will give you a wrong CFG. If you rely on this information, the instrumentation will not work and will give you false positives like crashes. So we actually built all the static analysis with the first step with IDA Pro, and we filtered out the erroneous disassemblies, some strange instructions. And for Adobe binaries, seems the compiler was pretty straightforward and the script works to the exact. So we can achieve almost 100% correctness. So sometimes for Microsoft binaries, sometimes we need to sacrifice a bit on the correctness. We can tolerate some false positives, especially for large binaries like MS HTML. There are actually considerable false positives. We have some heuristics to remove all the wrong disassemblies by IDA Pro. And it works very well on almost all Adobe Reader binaries. Normally less than 10 megabytes or up to 30 megabytes, like accurate 32.dll. It's around 30 megabytes and works very fine. Okay, Quynh will talk about the implementation of the instrumentation.
Okay, so next part is instrumentation. Because you see that for guided fuzzer, instrumentation is a core part, it's a very important part of a guided fuzzer. So how we did that? So remember that we want to build a fuzzer to run on many platforms and many architectures. So we look at on the public fuzzer, public guided fuzzer, and we learn some lesson. Because on the public guided fuzzer, they build on some public DBI like Pin or Dynamo. But there are many issues, as you can see. Pin and Dynamo, even after a very long time of development, they're still not very stable, not very reliable. And there are many limitations on platforms and architectures. So like on these DBI, if you want to make it work on other architectures like ARM, ARM64, MIPS, PowerPC, Spark, and so on, I think there's very little hope, right? And poor performance. Dynamo, as I said before, is like the best in terms of performance is still 15 to 20 times slow down your program. So we want to have something better. The reason on the guided fuzzer based on Pin or Dynamo are slow because they cannot do selective instrumentation. Because when you run your program under Pin, on top of Pin or Dynamo, it instrument on the program, right? So you cannot like selectively instrument a part of the program, but you need to instrument everything. And that's one of the reasons why guided fuzzer built on Pin and Dynamo are slow. So we learn on this lesson and we think that we need to do something differently. So we build our own instrumentation framework from scratch and we use hooking-based mechanism. So it's much more simpler, easier, and faster to build and to maintain. So hooking-based mechanism instrumentation is much more lightweight, and you can do selective instrumentation. So we want to instrument the whole program, and say that we want to focus on this part. We can only you can choose to only instrument this part, not the whole program, like as a DBI like Pin or Dynamo. But there's something you have to pay. You have to do offline analysis before you can instrument. So we know where to instrument, right? And that's what Quynh already explained. Okay, there are many types of hooking instrumentation, and just one very simple example. So on the left side, in the original program, okay, on the left side in the original program, you have this code. Now you want to instrument at that red instruction. To do that, we allocate one memory buffer, and we copy out that instruction to that buffer. And after that, next to that instruction, we put one call instruction, which call to our handler. And this handler in our fuzzer, we report back to the fuzzer. So it informs the fuzzer that already we reach here. So the fuzzer knows what's going on. And after that call instruction, we have another jump instruction. So when the instrumented program runs, it reaches the original instruction, it jumps to the buffer and executes the original instruction. And after that, it calls the callback handler. And after that, it jumps back to the next instruction. And that's how our hooking-based instrumentation framework works. Okay, so we build our own instrumentation framework named Scorpio. There are some features you can see. Scorpio works cross-platform. It works on all kind of platform you can find. That is Windows, macOS, Linux, BSD, and so on. It supports all the CPUs. Intel, ARM, ARM64, MIP, PowerPC, and Spark. We can use Scorpio to instrument at all kind of levels, in user space, in kernel space, and at instruction level. This one's a bit different from other public hooking framework you can find on the internet, because usually they only support to instrument at the function entries. But Scorpio allows you to instrument everywhere, not only the function entries. And Scorpio is very fast. Because we implemented Scorpio in pure C, we focus on low-level hooking mechanism, and it's super fast. With some very special setup, Scorpio can be 100 times faster than all the public hooking frameworks you can find now, thanks to many optimization we did inside the core of Scorpio. So how we build that? Remember that, go back to this slide. Okay, here to instrument that red instruction, we need to copy it out, right? So we need to know how many instructions, I mean, until when we copy, because like on x86, the instruction size is not fixed. So we need to know until when. We need to copy only one instruction now. In some simple case, some typical case. So to do that, we need disassembler, right? So Scorpio need to decode instruction at the hooking place, so it can copy the right instruction out until the right boundaries. So for this step, we use Capstone disassembler because Capstone already support on-cap CPUs. So for this step, Scorpio also support on-cap CPU like Intel, ARM, Arm64, MIPS, and PowerPC, and Spark, and so on. That is not the end of the story, because after we copy the original instruction to the new buffer, sometimes we need to relocate, you need to rewrite the instruction so it works properly in the new place. And for this step, you need to do some simple binary rewrite for code relocation. And for this step, we use a Keystone assembler, which is also viewed by me. And because Keystone also support on-cap CPUs, so Scorpio support on-cap CPUs. Intel, ARM, Arm64, MIPS, Spark, and PowerPC. And also because Capstone and Keystone are multi-platforms, so you can see that Scorpio also work on on-cap platforms, on-cap operating system. This engine allows you to install the callback. There has some API for you to install callback at any places in the program. And we support many type optimization and customization for on-cap requirements, so we can optimize your fuzzer as best as you can. We support many type hookings. We have many options for you to customize Chamberlain, and we support thread and internal memory management. So Scorpio work on on-cap operating system. Okay, so we use Scorpio to build fuzzer, Darko fuzzer to run on Windows, on Linux, and on Mac OS. For Windows instrumentation, we need to inject instrumentation into the target binary. So you can fuzz it, right? And here, to make it simple and easy, we put all the instrumentation code inside DLL, one DLL. So we inject DLL runtime into the target binary. And this DLL has DLL main, and this function is initialized before the main program runs. And inside this function, we do on-cap instrumentation inside this. There's something we want to tell. Because we want to inject the DLL into the target binary. There's two types of injection: dynamic injection or static injection. So we go with dynamic DLL injection. But there are also two ways of doing dynamic DLL injection. You do that at runtime using some like external process to inject, to watch, to monitor all the process running. And when your target program run, it inject it into the target program, right? That's one way. But we found that this way is not very good because we need to change the system. So we can inject DLL into the target program. You need to monitor all the processes inside of your system. So we decided to go with another approach, which is called static injection DLL. So the idea is that we modify the PE file. So we tell the PE file that we want to load one extra DLL. And what it is that we analyze the target PE to locate the section in the port directories, and we append one extra section into at the end of the binaries, and we relocate the import directory to the new section, and we point the original import directory to the new section, and in this new section we add one more DLL. So actually we modify the original program just to add one section and put one entry for our Darko instrumentation there. So when it runs, it automatically loads Darko.dll, and after that, everything is going well. So we find that this way works very well. Okay, for Linux and macOS instrumentation, we use another approach. We still try to inject the instrumentation at runtime, and for these platforms, we use LD preload mechanism, so you can dynamically inject instrumentation at runtime. So for Linux, we inject a share object file, which is .so file. For macOS, we inject a dynamic library, which is .dylib file. And similarly to Windows instrumentation, we inject all the instrumentation at the initialization time, at constructor time. And our fuzzer can support up to like 100,000 hooks, so we can imagine that we can inject like up to 100,000 hooks in some very big program into the target binaries when you try to fuzz that. So okay, so there's some details that we also support fork server in Linux and macOS. So we inject fork server at program entry points. Okay, so how about detecting crash? So we need to deal with detecting heap memory corruption, which is the main type, very important type vulnerabilities. So for Windows, we enable page heap for fuzzing target, and we do some kind of low-level exception handling, so we can handle exception from Windows core. For Windows and Linux, we do that differently. We had some built-in memory debugging inside Darko, so have better control and better performance. So for this type of memory debugger inside Darko, we overload on the memory management function like malloc, free, and so on. And we also utilize MMU, CPU MMU to detect errors like overflow or underflow. So we can detect bugs like op1, for example. And this memory debugger also can detect user after free error. Okay, there's some, you can see some demos, I mean some screenshots and understand how Darko works.
First we had run some simple experiments in the earlier version, the AFL sequence plus the pin probe mode. We tested on this 3D parsing library in Adobe Reader. So in around 10 hours, we find about, I think around 800 paths, and there are 2 crashes that were new at that time. One was a denial service, the other one was this memory corruption. To test the effectiveness of this fuzzer in handling binary parsing, because that's what the default AFL algorithm worked best in. We tested on an earlier version of Adobe Reader. We fuzzed this U3D parsing library. And in about 2 to 3 days, it's able to discover more than a dozen bugs, unique crashes. And of course, because I've done fuzzing in this library, and I know which CV it corresponds to. So here the list is those I know, and there are more. So the total number is more than a dozen. We will release those reproducers on GitHub as a justification that it's able to do complete coverage, almost like enumerating the code within a short time. We also tested on libxml2. This is a Windows port, an earlier version. We run 4 instances of the fuzzer. It finds 10 unique bugs in 1 week. Of course, those are also obsolete. Those are old bugs. We also found some bugs in Windows Journal, and this product is also obsolete. But this is just an example that this tooling is working. To find new bugs, we need something else to fuzz. Some of the current projects we test on medium-sized programs. libxml2, unfortunately, it doesn't support persistent mode because the default XML lint has a lot of global states. We tried with following examples with persistent mode on GDI+, on RA, MS XML, and Adobe Reader 3D. And this is a typo. It's the spider monkey JavaScript engine in Adobe Reader. This is fuzzing the XML, XML lint, the modified XML lint with the injected instrumentation. We can achieve about close to 90 per second on Windows. This is testing on RA. It's a bit small to check the exact numbers, but it's around 50 to 60 per instance. And Quynh also ported those EFL utilities to Windows to work with this instrumentation, the famous EFL tmin and EFL analyze. So this instrumentation at current stage is completely compatible to the EFL interface. Quynh also implemented.
Okay, so in this screenshot, you can see that on the we have two screenshots on left side and on the right side. On the left side, you see that this one we build Darko and we build Darko running on Linux. So it's a screenshot of Darko running on Linux. On the left side, we run the binaries in emulation mode, AFL -Q. You can see that the speed is like 800 something. 837 tests per second. On the right side, we run Darko using our own instrumentation, the same binaries, exactly the same binaries. And the speed is like 3272, which is like 4 times faster than emulation mode of AFL. So you see that, so it put us building the, our own fuzzer using our own instrumentation. This one's another screenshot. So you see that, okay, in this case, Darko run on Mac OS. So we have one simple test. We try to benchmark original AFL against our fuzzer. So on the left side, on the right side, we have some very simple test program, and we have source code. So we compile this source code in AFL on Mac OS, and we run these binaries on the right side of the screen. And you can see the speed is like 1,100 something tests per second. That's original AFL handle the program with the source code. And then we take the same binary and we run that binary inside our fuzzer. On the left side, you see the speed is like 1,010 tests per second. So you can see that the performance of Darko compared to original AFL with source code is like 90%. So just another screenshot. In this case, we run Darko on Mac OS. We run 4 instances at the same time in parallel mode. And in this case, we fast libxml2 on Mac OS. And you can see that the speed of one instance is like 500 something per second, tests per second. Okay, so we conclude our talks. So we say that Darko is an advanced guided fuzzer. We build from scratch using our own instrumentation frameworks. It's pure software based. We don't use any CPU support with Darko. So you can run Darko anywhere, in inside any virtual machine, for example. Darko support own kind platform and own kind CPU architectures, and we focus on fuzzing binaries. So you can fuzz a full binaries like what I showed before, and also we support persistent mode, so you can fuzz a part of the binary, not the whole binaries. And Darko proved to be very fast and very stable, and we really found some bugs so far. We are still working on that. We hope to report a lot more bugs in the future. So for Darko, we have no plan for what to do with that, but for the Scorpio instrumentation framework, we will release the framework to the public in the very near future, because it's still not perfect at the moment. We still need to work on that. So we'll see announcement on the public release of Scorpio in the future, probably in a few months. Okay, that's it. Any questions? Any questions? Yeah.
Hello, Theos, thank you. And I have a question about import address table patching. Could you please clarify a bit more? I mean, how do you deal with the delayed import?
Sorry, can you repeat your questions? How do you do
injection, import address table. How do you deal with delayed import? Oh, you don't? I mean, do you hook user32 functions, for example, on Windows? Or какого framework on Mac OS?
You mean delayed inputs to the program?
Yes.
Currently, we handle normal programs, but for special cases, I think specific engineering is needed to do that, to plug that into the framework.
Okay, thank you.
Okay, so one more question over there.
Raise your hand, please. Thanks for a very interesting presentation. As far as I understand, that you prefer a static injection in the Windows, yes? Is it right?
Now it's dynamic injection, but we change the original binary, so it automatically loads the DLL. So it's still dynamic injection.
It's how do you do it? Using by APC kernel or?
Okay, I go back to that slide.
I mean, there's several techniques to do it. It's APC or patching the original, as far as I understand.
Okay, so the point is that our information come in the form DLL, right? But still, how to inject DLL into the target binaries.
Yeah.
So the one way is that you monitor all the processes running. So when this one come up, you inject, right?
But how do you inject? Using what? Using kernel, APC?
No, but we don't use that thing. Use static injection. So, okay, we have this binary. We modify the binaries.
Yes, I understand.
Statically
so you prefer
on
static.
disk. Yeah. So it loads the DLL at runtime.
It's going from the import, I see.
Yeah, so see, we actually physically modify the binaries.
Okay, thank you.
So it's very simple. It works very well.
Yes, I understand. Thanks.
Any more questions?
Hi, simple question. Do you have TLS support? TLS, thread local storage.
Thread local storage?
Yes.
We use the TEB to store some of the thread-specific branching information.
Okay, thanks.
Thank you.
Yeah, our Fuzzer actually really support multi-thread programs very well.
Thank you, guys. You have a great job. My question is how much time you spend to do this Fuzzer, and how many people in your team?
Only two of us. And okay, only two of us. And here actually you can see that, okay, so to build this one, we need to have instrumentation framework first, right? So we already have capstone disassembler. We already have keystone assembler. We took few years to build that. And on top of that, we built our own instrumentation framework in Scorpio. And this took me like a few months to have the first version. But after that, we built the fuzzer on top of Scorpio, and it took quite a lot of time to clear all the bugs, to optimize the fuzzer and so on.
Okay, thanks. And one more question. Is your fuzzer works over network?
I think that's another, like, it's out of scope, right? Because yes, it works, but you have to write you need to customize Darko. So it works with network program. So yes, it works, but you need to do quite a lot of work, and it also depends on the binaries you want to fuzz. So different between different programs.
Okay. What kind of customizing I need to do?
So it is a little bit different. So far we have some tests in Linux. Something similar, what I can think of is to build something like the DSOC approach. We change the socket APIs for the userland network program and make it local. Then we make use of the original network iteration for the loop. That's what I can think of, because we only tested this on Linux. It works fine. On Windows, we haven't tried, but we believe the similar approach will probably work, but we haven't tested yet.
Thank you.
I'm going to add support of Windows kernel fuzzing.
Can you repeat your question?
I'm going
kernel fuzzing?
Yeah.
Actually, I think the similar approach can work, but just a bit different, right? So like FL, you cannot use FL to fuzz kernel, right? So there are many, recently I saw many new fuzzer using the same guided fuzzing techniques introduced by FL, but they make it work for kernel fuzzing. But they use quite different techniques, like you need to run the fuzzer under the whole system, like in the hypervisor layer. And yes, it's quite different. But the same technique works, yes.
And one more question. Is it possible to divide the fuzzing task for one application onto different computers? So, like mining, you know, you take one application and divide different patches of fuzzing. And one computer is working with another, one patches, one with another.
Do you mean the parallel fuzzing?
Is it possible? Yes.
Yes,
Yeah.
fuzzing by its nature is parallelizable.
You can look at this screenshot.
Because you actually only deliver the test case generated,
So
and the task itself is parallelizable.
So you can do something like mining, but fuzzing, and make a result of a lot of tasks running in parallel. Yes?
Yes, we can run
it's
it
possible,
in parallel.
yes.
It's by itself, fuzzing can be very
So
well parallelized.
Cool, thanks.
So you see that on this screenshot, we run 4 fuzzers at the same time, and they work on the same binaries.
I see.
Yeah,
Thanks.
same target, fuzzing the same thing.
That's all? No questions?
No more questions? Okay, the last one.
One more.
Thank you very much for your presentation. I have a quick question. This tool is already available on public, or you guys still developing?
No. So as I said in the last slide, we release the instrumentation framework named Scorpio to the public in the future. Maybe in few months, we still need to work on that.
Okay.
But for the further, we are not sure yet.
Thank you very much.
It is actually very easy to build with this instrumentation.
Yeah, you can try yourself. Okay, so thank you a lot for attending our talks. Thank you.
Thank you.